What's up, guys? Today I'm going to make a video about factorials and assortment of objects in a set. So I think the easiest way to explain this is starting off with an example. Say we have one object, right? This is a circle. Now, if I ask you the question, how many ways are there to arrange this? You might say one. And this kind of sounds like a dumb question. It's one object, one way to arrange it. Alright. Easy enough. Now if I have two objects here, how many ways are there to arrange it? Well, there's one right there. And one right here. Alright, so for two objects, it's two ways to arrange them. Now it starts getting tricky when we have three. Alright, there's one way to arrange three distinct objects. Okay, well, another way could be circle still in front. And we switch that triangle and square. Alright. Now I could put the triangle in the middle. There's no particular order to these. Alright, that's three ways. Is there another way we can do it? Let's see. We could try this setup with the triangle over here, except we switch the circle and square. And we haven't had any arrangements with the triangle in the front, so let's do that too. Alright, I think that's all the ways we can arrange those three objects. Turns out to be 6. So there's 6 ways to arrange three objects. Now, what about 4? How would we do 4? Well, instead of doing it this way, where we just try to exhaust all possibilities by brute force, there's a trick we can use. And that trick is, alright, we have the original 3 objects, right? And we know that there's 6 ways to arrange these guys. And let's say we have a 4th object. I'll make it some kind of star thing. I don't know. Alright, so we have a 4th object over here. Now what we can do is we can say, alright, let's fix that 4th object right here. So if we fix the 4th object at the end, right here in this first position, then there's 6 ways to arrange the other 3 objects. Okay. Now let's stick the 4th object here, where we have 1 object on this side and 2 on that side. Well, then it again reduces to the case before of 6 ways to arrange that. If we stick it the 3rd position here, again it reduces to the case of arranging 3 objects because it's stuck at the same location. And finally, on the other end, there's also 6 ways. So 6 plus 6 plus 6 plus 6 equals 24 ways to arrange 4 objects. Now if we have n objects, we might realize, okay, let's get a little more rigorous here. I'm going to use, let's see, I'm going to use O1 for object 1, 2, O3, dot, 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 to ON. Actually, let's make this ON minus 1. And then we have some additional ONth object over here. Alright. So, and let's call the number of ways to arrange n objects f of n. F of n is the number of ways to arrange n objects. So, I shouldn't have drawn it there. Put it up here. F of n, number of ways to arrange n objects. And we know that this is f of n minus 1, because there's n objects. Now, using a similar argument that we used for the case of 4 objects, we can say, alright, how many ways are there, if there's f of n minus 1 ways to arrange n minus 1 objects, how many ways are there to arrange n objects? Well, we could put the additional nth object right here, and that'll be f of n minus 1 plus f of n minus 1 right here, and all the way down turns out there's n ways, n places or spaces in between all these objects to put this nth object. So we get n cases of f of n minus 1. So that turns out to be, there's n times f of n minus 1 ways to arrange this set. Alright, and we can then see that, oh, there's n objects here, and we're looking at for the number of ways to arrange n objects. This gives us the relation f of n equals n f of n minus 1. Well, that's neat. We know that for the nth object, it's just n times the number of ways to arrange n minus 1 objects. And we can use this formula recursively and get n times n minus 1 f of n minus 2, right? Because we're just plugging in the argument for this original formula back into here. And if we keep doing this, it's n times n minus 1 times n minus 2 dot 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 3 times 2 times I ran out of room 1. And this looks familiar. This is the definition of n factorial. Although there is a little bit of, I guess, nuance in the philosophical case that n equals 0, because 0 factorial is 1. I guess you could argue there's one way to arrange 0 objects, but in general, for n is a positive integer, this makes intuitive sense based on our derivation up here. So that's where that comes from. The number of ways to arrange n objects is n factorial. My next video I will go over the binomial and cases where objects are similar and they're not all unique. Thanks.